Aloha everybody, this is Gigi from Kauai Community College. This is a video lesson on what the derivatives will tell us in terms of a graph of a function. Okay, so let's get started here. First thing first, we're going to have a definition of what it means to be increasing. A function is increasing if f of x2 is greater than f of x1 whenever x2 is greater than x1. Now, that is a mouthful, right? I'm going to put a picture up and then you'll see what I mean by that. What this is all mean is if you are moving from left to right, meaning x2 is greater than x1, right? If you have that, then what will happen? Here is f of x1 and here is f of x2. What we're saying is as we move from left to right, if our function value is going up, meaning if f of x2 is greater than f of x1, whenever x2 is greater than x1. If that's the case, then the function is increasing. Okay, so moving the x value moving from left to right, the y value will be moving up, and that is when your function is increasing. Now, if we do look at the derivative of an increasing interval, let's look at the slope of those tangent lines. The slope of those tangent lines are positive, right? Going uphill. The lines are going uphill. So the function is increasing when the derivative is greater than 0. Okay. Likewise, your function is decreasing if f of x2 is greater than f of x1 whenever x2 is greater than x1. So x2 greater than x1 is meaning to say that x2 is to the right of x1. x2 is to the right of x1. Then our function value here is f of x1. And here is f of x2. As you can see, when we are moving from left to right, the function value is going down. So that is when we say our function is decreasing. So that's the definition, right? Now, if we were looking at the slope of the tangent line of a decreasing interval, what do we notice about the slope of those lines? Those are downhill lines. So the slopes are of negative value. That means that the function is decreasing when the derivative is less than 0. So that is what the first derivative tells you. The interval in which your function is increasing or the interval on which your interval is decreasing. Now, the first derivative test will tell you this. If you assume continuity and differentiability within that interval, if the derivative changed from positive to negative through some point C, meaning if your function is increasing and then decreasing, and here is your point C, then what can we say about that part right there? That is your local, or we call it relative maximum, right? So if your derivative changes from positive to negative, then you have a local maximum. And if you go the other way around, if your function is changing from negative, that means if your derivative is changing from negative, that means it's decreasing. And then it's increasing, then we would call this right there your local minimum. Okay, so if again, this would be where your point C would be, right? Okay, now what if your derivative doesn't change in sign. If the derivative didn't change sign, then we don't know. We don't know. No local or extreme value right there at C. It's neither a maximum or a minimum. So that's what the first derivative will tell you, and that stems from the fact that that if the derivative is positive, then your function is increasing. If the derivative is negative, then your function is decreasing. So if you have a change in sign, you must have a peak there. Okay. Now, here is an example. Okay, the function for the population of rabbits is governed by this function. P of t is equal to that right there, where t is in years. Okay, the unit of t is in years. Okay, now determine if the population will ever decrease within the first 2 years. That means, will your derivative ever be negative within the first 2 years? That's what the question is asking. The first 2 years would be the closed interval from 0 to 2, right? That's the interval we're looking at. Now, take the derivative, clean up the derivative, and then factor out the t. We have that. So your critical point would be when t is equal to 0, or when 2 ln of 3t plus 1 is equal to 0. When solving for t, you will have these two critical points. This number right here, if you type that into your calculator, it would be approximately 0.2. Okay, so what are we going to do with those critical points? We would put them on a number line. And then here, we're talking about the number of years, so we're not going to have negative value. You're just going to start at 0. And then time will move on, right? And we're really looking at this interval right here. The question is, will your derivative ever be negative? Meaning, will your function ever be decreasing within those first 2 years? So what we're just going to do is go ahead and plug in some values and check the derivative. And that should be p instead of f, but you know what I mean by that. The first derivative evaluated at 0.1. If you type it into your calculator, you will have a positive multiplied by a negative, which is a negative. So your function is decreasing right there from 0 to 0.2. And then between 0.2 and 2, let's pick 1. So the derivative at that point would be a positive number. So your function is increasing right there. So you have really a relative minimum right there. Okay. And then if you test on the other side, the function value is positive, so that is also increasing. But in the interest of answering this question, determine whether the population ever decreases within the first 2 years. And the answer is yes, right here within that interval from 0 to 0.2 years. Now, it seems kind of weird to talk about 0.2 years, right? You're not going to like come up to somebody and say, oh yeah, the population was increasing for the first 0.2 years, right? So let's talk about realistic units here. Do a little unit conversion, 0.2 year, 12 months in a year, and then 30 days in a month. So you will have approximately 72 days. So you would say that the rabbit population decreases in the first 72 days, and then it's going to keep increasing after that. So really that relative minimum right there really is your absolute minimum, because that is the only place where it's going to dip down and then it's going to keep going back up all the way. And that is an application of the first derivative and the interval of increasing or decreasing. Okay, now second derivative. What does the second derivative tell you? How your curve is curving, meaning the concavity of the curve within that interval. Okay, so if the second derivative is positive, then your function concaves up. So if the second derivative is positive, then your function concaves up. That is when you have a happy face. Okay, now if your second derivative is negative, then your function is concaving down, and that is when you have sad face, concave down. Okay, the point where your concavity changes right here is called the point of inflection. Point of inflection. And I will just call that POI for this class. Point of inflection. All right. Let's do some specific example there. That was too many S for me to say. So here's your function. First derivative, second derivative. Factor out the second derivative. We will say that the second derivative is 0 when x is 0, negative 1, and 1. Put those on the number line. Okay, and what are we going to do? We're going to test to see the concavity of the graph. Okay, so f of negative 2, which is to the left, is a negative number because negative 2 times 30 is negative. Negative 2 plus 1 is negative, and then negative 2 minus 1 is also negative. And if you multiply 3 negative numbers, you will get a negative number. So your function concaves down to the left of negative 1. And then if you plug in a number in between negative 1 and 0, say 0.5, you will have a value of a positive number. So your function concaves up in that interval, which means negative 1 is a point of inflection. That's when your concavity changes. Okay, now let's plug in a number between 0 and 1. For example, 0.5. And plug that into the second derivative, you will get a negative number. So your function concaves down between 0 and 1. Again, you will have a point of inflection here because that is when your function changes in concavity. Okay, and then plug in a number to the right of 1, let's say 2. You have a positive value for your second derivative, so your function concaves up. That calls for POI right there. Point of inflection, where concavity changes. So to answer the question, when is our function concaving up? It will be concaving up within the interval from negative 1 to 0 and 1 to infinity. Your function concaves down in the left and in the middle, which would be negative infinity to negative 1, and also from 0 to 1. And then one thing that concavity and critical point will tell you is this. If you have a critical point, say this point right there, and say that is C, right? Or this point right here, and let's call that point, I don't know, that's C1 and this is C2, and let's say this is C3. Okay, so what's going on at that particular point? If you have gone and found your critical points to be C1, C2, and C3, those are your critical points. If you plug that number into the second derivative, and that turns out to be positive. And if that turns out to be positive, you have a thing that concaves up. And so you have a bottom. You have a smiley face and you have a bottom. So that gives you a local minimum. Okay, now let's focus on C1. If that is your critical point and you plug C1 into your second derivative and it becomes a negative number, then at point C1, your curve is concaving down. And if your curve is concaving down, you have a sad face, and that will be your local maximum. You have a peak, you have a top. Okay, and that's what the second derivative will tell you. So in terms of your local max and your local min, you could use the first derivative test and look for the change in sign, or you could use the second derivative test and plug in that critical point into your second derivative. So that requires you to take the second derivative and then plug in the point. It's up to you how you would like to use it, and it depends on whether the function is easy to take the second derivative of or not, right? So that's a choice that you have there, but that's the second derivative test. And second derivative tests also say that if your second derivative evaluated at that point is equal to 0, then we don't know, right? So don't make any conclusion if your second derivative is equal to 0. We don't know. It doesn't say that it's a point of inflection. Remember that. We just don't know. All we know is if the second derivative evaluated at that critical point, if that's positive, then you have a minimum, because if you visualize it, that curve right there is concaving up, so you have a bottom. Okay, so that's the second derivative. Now let's go and use it. The function is sine square x. So then the first derivative is bring the 2 down. Okay, so you have 2 sine x, inside derivative is cosine x. This is an identity right here. 2 sine x cosine x is really just sine of 2x. So your critical point, or the first derivative, is equal to 0 when sine of 2x is 0. So 2x must be, so when is sine 0? Sine is 0 when, let's look at your unit circle here. Sine is 0 here and here, right? So if you think about it, that's 0. That is pi, and 2 pi, and then you keep going, that's 3 pi, and so on. That if you were going in this positive direction, right? And if you go this direction, you will have the negative direction, but still it is 0, negative pi, negative 2 pi, and so on. So that is why I wrote 0 plus or minus pi plus or minus 2 pi, and so on. And if you were solving for x, then you have to divide everything by 2. So really, we are looking at these points right here as our critical points. That would be pi over 2 and 3 pi over 2. Okay, and it's plus or minus. You can go in either direction. Okay, now, sine of 2x is something that's easy to take the derivative of. So we could just go and find the second derivative. The second derivative would be cosine of 2x multiplied by the inside derivative, which is 2. Okay, so how are we going to use the second derivative test to find our relative max and min? We're going to plug in these critical values into the second derivative. So the second derivative evaluated at 0 is 2, and 2 is greater than 0, so we have a thing that opens down like that, and that gives you a local minimum. And then when we plug in either positive or negative pi over 2, you will have the cosine being actually that is -2 because cosine of pi is -1 times 2 is -2, which is a negative number. A negative number concaves down for the second derivative. So that point right there is what we call a local maximum. And I think the process will repeat itself and your values would be alternating. So when you plug in pi, you would have 2, which is a positive number, so it will give you a local minimum and so on. So it looks like your function, and if you look at the graph on decimals or whatnot, you will see that at the half, then you have your maximum, okay, and then at the whole pi and 0, you will have your minimum, and that is how we use the second derivative test to determine whether a function has a local max or min. And that is it.